All right, we are live. Hey everyone, thank you so much for joining us today for the Hoodie Community Sync. We'll give it a couple minutes, like a minute or so, and we'll take it from there. Let us know where you're joining in from today, and if you're building lake houses with Apache Hoodie or lake houses in general, and have questions around it, be sure to follow our LinkedIn page and post out any questions in this event as well. So in a minute or so, we'll just get started with our today's presentation. All right, I think I can see some people joining in, so that's good. So we'll just get started with our today's agenda in general. So hi everyone, and welcome once again to the Hoodie Community Sync. If you are new here, Community Sync allows community users and developers to meet, interact, and exchange ideas on Apache Hoodie and how it is implemented in various organizations for their data lakehouse architecture. Today we have yet another interesting presentation from Kuaishou's data platform team. If you haven't heard of Kuaishou, it's a video sharing platform, social network that is powered by data and AI, and specifically Apache Hudi. And during this presentation, our speakers, Zhong, Liang, and Yang Hao, they are big data architects at Kuaishou, and they will introduce a high-performance lakehouse system, which is capable of second-level data freshness, petabyte scale storage, and terabytes read and write throughput. They will basically share how they tackle the technical challenges in building and scaling the system to meet the demands of data infra for AI workloads. Before we go into that, I'm going to give a quick rundown of the community stats since we last met. So in the last month, we have had around 119 PRs, which is a lot, and that means a lot has been brewing on the Hoodie project side. And we have had like 43 developers who contributed to these PRs. We also have like close to 29 issues during this time, and there are also new PRs being worked on right now. So a lot of momentum in general with the project. In terms of the community growth numbers, quickly, we have over 4,689 plus users on Hoodie Slack today. And Slack is a great place for the Hoodie users to bring up any discussions, issues while implementing Hoodie. Knowledge guides are shared. There are PMCs to chat. So, you should definitely take that opportunity to join Slack and, be a part of the community. I will share the link in the next slide for you to join. There is also a QR code that you can use to scan and join the Slack group. On GitHub, we have around 5,700 plus stars, which is really good momentum in a way. And if you haven't already given us a follow on LinkedIn and Twitter, please also make sure to follow that. We always post the latest updates and what's happening in the world of Apache Hoodie and Lakehouses in general in those communication channels. You can also start us on GitHub if you like the project and you love and use Hoodie. And this is the QR code if you want to just scan and join the Slack community. With that, let's welcome our speakers. I'll basically get them to stage and take forward with the presentation.
Hello, everyone. We are honored to present Kuaishou's Evolutions of Data Infrastructure for AI Scenarios. The session will be delivered by myself, Zhong Liang, and Yang Hao, data architects at Kuaishou. I have led the integration of AI scenarios with Kuaishou's internal data lake ecosystem, and the new architectures has been successfully implemented to production with significant results. Industry applications of data lakehouse primarily focus on BI scenarios. Kuaishou has extended this function to AI scenarios, which surpass BI in both cost scale and application scope. While the application patterns align between BI and AI scenarios, there remain significant gaps in implement requirement. The upgraded architecture addresses three key improvements. One, unified production instead of fragment process. Two, Open Lakehouse interface, replacing closing technical components. Simply near real-time data flow over complex conversions and delayed processing. By establishing the AI data lake storage foundation, we unified real-time computation in 3 points, integrated massive heterogeneous data, and enable multi-engine processing with flexed consumption modes. For example, AI data lake, your single gateways to both live data streams and years of code storage, powering everything from real-time trading to circle querying with bundling superpowered like smart merging and filtering. No more jungling Kafka, HDFS, and a dozen tools. The new architectures delivers substantial benefits, result saving in production, reduced training costs, improved data timeliness. It's from offline to near real-time, and efficiency gains by orders of magnitude. This transformation has yielded substantial benefits. We have slashed compute by 10%, storage by over 50%, cut training bandwidth and CPU used by half, and 20% while boosting model interaction 2.4x, and finally making analytics near real-time from hours to minutes. Today's presentation will cover 4 key areas: AI data usage, paradigms, and challenges. 2. Architectural evolution with Lakehouse. 3. Implementation, collection, and solutions. 4. Future roadmap. Part 1, 2, 4 is covered by me, and part 3 is presented by Yang Hao. Our AI medical how the brain knows, crouching mountains of user behaviors data, like Kuaishou, 100-minute DAU videos, to predict a trend, while models involve the life with error scroll, click, and watch. Kuaishou AI applications like video recommendation, e-commerce recommendations rely on model training for good results. Key metrics include click-through rates, conversation rates, and watch time. Training data involves 2 modes. 1. Integrated storage. Sample and features are stored together for real-time model prediction, enables real-time predictions. 2. Separator storage. Models use existing data for prediction, while iterative training combines new feature with historical data. No more shifting through all the data columns. Our models training cherry-picking only the critical future needs, exactly when they matter. Data flows into TensorFlow frameworks with strict non-repetition requirements to avoid overfitting, but it along the partial discards. Training data follows in macro batches for vectorization 6 seconds, and let us stitch future with columnar. As long as the data columns line up like puzzle pieces, the current infrastructure use Flink to merge sample data into MQ for real-time training, while offline data is stored in HDFS for cold start, modules, and analytics. Additional offline tasks mixing base sample with warehouse data, then serve them two ways for offline training or ready-to-use datasets for deeper analysis. Exciting big data frameworks hit snap with AI storage and compute needs. Cracks in the system that add up fast. Our AI infrastructure jungle storage lawyer, MQ, HDFS, and object storage, but duplicated data in MQ and HDFS burns cache, and real-time trading paints conversion text to flake row to base stream into column fuel. Our compute flow tangle API and event data into two pipelines. Offline analysts scroll through stale datasets while real-time trading stages stream in on the fly. This fragmentation traps insights in slow motion analytics slide to databound data. Let's untangle the core pain points. Plugging today AI data architectures, we got computational headaches with foundation compute and storage loads meet inconceivable sample handling, creating data across pipelines, architectures each tied to different components turn latency into take depth hell. We also had storage woes, low row-level compression, bandwidth hemorrhage. The row-to-column shuffle slaps a heavy CPU tax, while Kafka data row-based stream to column diets CPU bottlenecks cap throughput. Model interaction becomes a thread mill. Live data trickles in. Off data lags by hours or days. Need massive data. Prepare for snail pace upgrades. Kuaishou's AI workflows get stifled by legacy data system. To drive a Lakehouse powered overhaul at AI scenarios, we must deeply align upgrades with our model training use cases, pinpointing exactly where and how next-gen architecture can supercharge efficiency. Building on the pain points outlined in the previous sections, let us now consolidate the key takeaways. We had this strategic vision. 1. Stream batch. Unification is best. Merge streaming and batch realms with incorporate SLA, one compute lawyer, one choose. Training models on fresh data without latency jitteries. 2. Low cost. Slash the quadruple bundle CPU, bandwidth, compute, storage, architectural overhaul meets smart data patterns to stop the result hemorrhage. Turbocharged data muscle. Group big scale real-time streams enable faster speed future experimentation. Master data with automatic updates and read and write, scaling that at PB. Why Hudi? It is a simple choice. Hudi's streaming first design check out non-negativables, unify streams ingestion or writes. We bye-bye to batch stream separators. Results like ordering for training. There are no CPU fireworks anymore. Kuaishou turned latency. Minutes level deliver now. some minutes insight. In our data lake, interaction already proved the leap. When use Hudi in action, we got the architecture blueprint. Developing Hudi as our data lake backbone enables next-gen workflows. Real-time ingestion with Flink generates flexible feature engineering, switching feature with context-aware compute engines, unified training data service, fresh sample and features accessible across batch stream modes, data analysis with booting screen evolution handling. Nevertheless, the critical change lies in operational this compatible within our application stack. For example, within our application stack, for example, achieving sub-second SLA, complying for real-time model training, bridging batch processing semantic with stream API architectures, detecting details, updates in real-time data lake for analytical workloads. Next, we will provide a detailed explanation of the main scenarios. First, let's see real-time training. It's the 13-second rates. By leveraging high throughputs batch workflows, we achieve the training throughputs that overperforms real-time role-based data pipelines constructed by sub-second latency requirement. First is lightning ingestion. Clean stream data and future reflow converge in Flink right to Hudi tables, data and metadata with sub 20 seconds latency. Next, faster training. Try jobs pull metadata and trigger file features. Feed pipelines within 10 minutes or 10 seconds. This case has some key enablers. 1. Streaming writers. 2. Polyglot access. 3 is multi-stream rates and row corner pruning. The last is second-level freshness. This is a case that offline training with bounded stream. The data pipeline support dual modes, real-time streaming to Hudi data table, and offline future correction when spec drops. Corrected future states are subsequently persistent back to Hudi table for historical consistency. Library awareness, unified metadata tracks the real-time offline datasets. Time range selects smart metadata scan which precedes data windows. Columnar stitching on read, batch data transformed to optimized formatted during retravels. At the last, critical compatible to unpack. Offline future pipeline, bounded stream consumption patterns, and the column optimized tricks. We have optimized the system for analytical workloads with current production support for batch processing. Details, architecture, and benchmarks follow. Minutes level analytical, querying copyright table when blind. Its core is Doris, always on Spark Circle. Ad hoc querying with white table joins across real-time offline data. Schema update. Automatic data resharpening during RAID to handle evolving schema. How did we crack those architectural and scaling nightmares to shape it to be elaborated by Yang Hao, covering implementation, handle, and technical revolution.
Hello everyone, I'm Yang Hao. Thrilled to be here today. In this session, I will walk you through the iterative journey of our technical implementation, from establishing basic read-write functionality to meeting data quality requirements and ensuring system stability. Well, we faced numerous challenges along the way. Given time constraints, I will focus on key case studies to illustrate our progress. The most fundamental function of the system is data ingestion and egress. In the following section on data timeliness, I will detail the adjustments we made for data ingestion. Therefore, here I will focus on how we implemented data reading. Unlike BI scenarios, where data analysis is based on circle rates, in AI scenarios, the data reading nodes for model training are mostly implemented in non-Java languages, such as C++ for Kuaishou's model training. Thus, how to achieve cross-language reading of Hudi tables was a challenge we faced. There were three optional solutions. First, each work reads Hudi via JNI. Second, each work implements a C++ reader to read Hudi. And the last one, use a proxy service with Hudi and then distributes the data to each worker. In the first two solutions, each worker accessing Hudi involves a large amount of metadata concurrency, and the reader is bound to the worker, which is not conducive to future expansion of multi-data reading. Moreover, developing an independent C++ reader requires significant modifications and high development costs. Therefore, we adopted the third solution as our reading architecture. Next, we faced a critical design choice: use row-level with file-level distribution. For row-level distribution, there are fine-grained load balancing, but lacks column pruning. For file-level distribution, it enables batch processing and columnar optimization. For model training, where data is batched in memory before computation, file-level distribution proved superior. Workers load the entire file slices and eliminating pair-row accumulation overhead. Columnar storage, such as Apache, can further allow pruning unused columns, minimizing I/O. Thus, we adopted a file-level distribution with metadata interfaces for batch rates. By deploying an independent meta-server service, we have supported cross-language reading methods, meeting the basic requirements for cross-language reading. Furthermore, based on this independent service, we have implemented many flexible reading strategies, including a single training task can read multiple Hudi datasets, and the same data source can be read by multiple tasks. Multiple data sources can be combined using union and join operations during reading to concatenate data. Data can be evenly distributed based on the number of reading nodes, which can also implement balanced data distribution. For streaming consumption, we support incremental consumption similar to Kafka, allowing users to define flexible time ranges for data consumption, such as delayed consumption. Before data distribution, files can be flexibly adjusted to meet downstream requirements for data order, such as random or ordered. Well, these features are made possible by using a dedicated server service for data distribution, and that is why we chose this reading architecture. This session, I will introduce our work on data timeliness in data quality. Real-time model training has high requirements for data timeliness, with end-to-end latency needing to be within 30 seconds. However, vanilla Flink to Hudi workflows pose the following issues. There are redundant shuffles during writes, raw column conversion overheads, and slow instant creation and commit processes. To address these issues, we have modified the writing mode, writing operators, and instant acceleration methods. So let's look at the specific steps we took. First, eliminating shuffles. Since our log streams requires no updates, we remove the shuffles to cut network overhead. To prevent bottlenecks in the single-thread Hudi sync operator, we introduced multi-threading within the sync, evenly distributing data across threads. Thereby, it can achieve horizontal traffic scaling. Next, asynchronous flashing. For at most advanced semantics, we decouple in-memory data organization from file flashing. By making flashing asynchronous, we snatch the I/O wait times, boosting throughput. So what's the result? We got a shuffle-free, non-blocking write pipeline with minimized I/O latency. Currently, Hudi's writing process still uses raw-based writing. When using Flink for real-time writing, raw-based data needs to be converted to every format Hudi records, and then written to Parquet using every Parquet writer. When our data source is columnar, it needs to be converted from columnar to raw-based in memory, and then back to columnar for writing. This redundant raw column conversion results in low writing efficiency. To accelerate the performance of the writing operator, we consider the vectorization techniques, which can speed up computations. Given that Rust has excellent ecosystem support for Arrow and Parquet, as well as its superior memory design, we implemented columnar writing to Parquet using Rust, which improved our performance by over 60%. Okay, then let's dive into a common challenge with real-time Hudi ingestion. That is periodic throughput fluctuations caused by Flink checkpointing mechanisms. Specifically, each checkpoint execution causes a temporary drop in write throughput. The issue stems from that a real-time writing job can only maintain one in-flight instant at a time, and the job manager must wait for current instant to complete before creating the next one, which involves synchronous waiting for all task managers to finish writing the current instant. For task managers, after organizing and submitting data for the current instant, they must synchronously block until the next instant is generated, which involves loading the latest timeline to check for new instants, triggering get list requests to the HDF's name node. However, different task managers have varying processing speeds, so those that complete early must wait for others to finish writing the previous instant, causing blocking and affecting performance. What's more, each task manager independently loads the timeline to get instance, resulting in numerous concurrent get list requests to the HDF's name node, causing stability issues. Therefore, we wondered if there is a way to distribute instance and data to each task managers. This would eliminate the need for concurrent timeline loading by task managers and remove the synchronous waiting for instant acquisition. So we leverage Flink's checkpoint barrier mechanisms to distribute instance here's how it works. When a checkpoint is generated, its time step is used an instant and created and job manager. The checkpoint barrier carries its time step, and barriers flow through the data pipeline. Each TM extracts the time step from the barrier. So in this way, task managers no longer need to block waiting for instant acquisition. They derive it directly from barriers. And task managers no longer need to node timeline to check for a valuable instance too. Thus, it can avoid get lists. It can avoid get list requests to the HDFS name node. So let's see how our job improved after adjusting the instant acquisition way. From a throughput perspective, since task managers no longer need to synchronously wait for the next instant after taking snapshots, job throughput increased, and the throughput curve becomes stable. Moreover, since task managers no longer actively call get list to access metadata directories, the number of requests to the HDFS name node decreased significantly, reducing the load on the name node. After addressing data timeliness, we encountered another data quality challenge during the system's deployment. In some scenarios, switching the training data source from Kafka to Hudi resulted in a decrease in AUC metrics. Analysis revealed that Hudi data rates caused data disorder, which in the context of model training would cause the model to learn incorrect data and degrade the training results. To assess this disorder, we established a disorder matrix and attempted to optimize it by adjusting the writing mode. Results showed that the disorder value of data read from Kafka was much lower than from Hudi. So we analyzed why Hudi data source caused disorder. And this disorder is temporal, meaning data is out of order in terms of type. And shown in the diagram, to achieve node balance, each work reads data from a fixed Kafka partition or files produced by a fixed task manager in the Hudi table. When reading directly from Kafka, data in a single partition is ordered, so there is no disorder for read Kafka. However, when reading through Hudi, data is distributed across multiple threads during ingesting, causing temporal disorder between files produced by the same task manager. When reading nodes read multiple files, overall data becomes disordered. Therefore, while data within files is ordered, data between files is disordered for Hudi source. So to avoid disorder caused by data writing, we optimized the data organization mode to ensure relative order between files. And how we do it? Like task managers maintain high throughput while ensuring relative order between multiple output files is difficult. And the solution is we use the multiple threading. But with a difference, we catch the data for each file in memory and process it in batches to ensure order between files. For example, we catch the data from rows 1 to 1000 for thread 1, and data from rows 1001 to 2000 for thread 2 in memory, and then process the cached data asynchronously. So this is a space for time strategy. By implementing this combined with the file name-based distribution on the middle server, we achieved ordered data consumption and successfully applied it in scenarios that requiring data order. Next, I will introduce our work on stability. In production scenarios, multiple models simultaneously read the latest data from a Hudi table, causing high traffic data access, which is challenging for HDFS servers. Besides, machine-level issues like band nodes and slow nodes affect writing, and job-level memory over limit happen frequently, and metadata operation latency increase over time. So to address these challenges, we made corresponding optimizations. To support model training, we need to provide data for both online and offline training. Online training, that is, require the most recent data, such as data from the past hour, with read throughput reaching TBs per second. For offline training, that requires historical data, such as data from the past 2 weeks or even a month. This is netting long-term storage and PB scales. And the same Hudi table data is accessed by multiple training tasks. So to achieve such a high throughput and long-term cost-effective storage is a significant challenge. Internally, we use HDFS as the underlying storage system for Hudi, with storage media options include SSD and HDD. SSD provides high-speed read-write capabilities but are expensive, while HDDs are cost-effective but slower. By combining their strengths, we offer a cold-hot tied storage service. Specifically, we use HDFS cold-hot tied storage service to optimize data storage, meeting different read-write requirements while reducing storage costs. Data is initially stored in SSD cluster, leveraging SSD's high-speed read-write performance to provide stable write throughput and meet real-time trains hold data rate requirements. For historical data, such as data older than 1 hour, is automatically migrated to HDD cluster according to predefined policies. The advantages of this approach include handling real-time hold data with the SSD cluster and provide high-speed read-write performance for real-time training, which is what's called online training. For storing historical data with the HDD cluster, it can reduce storage costs and meeting long-term storage needs for offline training, and can also use it for AI business analysis. In actual production scenarios, machine issues frequently arise, impacting stability, which can be categorized to band nodes and slow nodes. Due to time constraints, I will focus on slow nodes here. Slow nodes can be categorized into Flink computation slow nodes and HDFS storage slow nodes. Computation slow nodes refer to task managers in Flink that with poor processing performance and needing to lag in some partitions. In the context of model training, models can tolerate minor data loss. So we add a feature to proactively discard lagged data. When data lag occurs due to slow nodes, a certain percentage of data can be lost to ensure data freshness. Moreover, Flink implemented an intelligent detection of slow nodes based on business and machine metrics, and can evict or blacklist abnormal nodes. Well, these mechanisms help mitigate the impact of slow nodes. And Due to our asynchronous handing of file writes, there is no need to synchronously wait for data to be flashed. However, data availability requires synchronous waiting for file completion too. Considering the goal of high timeliness, we discard files that exceed the write timeout to ensure timely submission of the instance. Well, during real-time writes, each task will create files in the same directory, and our tasks have high concurrency and timeliness. The HDF's name node needs to handle a large number of concurrent modification requests in the same directory, leading to several log contention and affecting HDF's name node response times. So to address this, we split partition data directories using hidden subdirectories, which can reduce local granularity and elevating directory local contention. Absolutely, user can also read the data as before too. Despite splitting directories to elevate local contention under high concurrency, we also independently deployed a name service to prevent abnormal access in other channels from affecting our service. Another common stability issue in real-time writes is tasks being killed by scanning system due to memory out of limit. To reduce the risk of tasks being killed due to memory limits, we implemented a memory control strategy to avoid memory overflow. This involves periodically checking current memory usage and stopping data input if it exceeds a set threshold until memory usage decreases. This can effectively reduce the risk of memory overflow. Okay, last, Hudi's metadata archiving strategy significantly impacts read-write performance. Over time, the number of instances increases, leading to high latency in building timelines and related operations during writes. Therefore, we need to archive metadata. To provide efficient instant metadata retrieval after archiving, we introduced the LS tree timeline from one reservation, reducing the number of archived files and improving querying speed. Additionally, since our meta server handles data distribution, it needs to load and parse the timeline and the instant metadata for file size distribution. Large amount of metadata can slow down the loading and parsing process and may cause out of memory. Therefore, we implemented incremental loading to avoid OOM problems during metadata loading. Okay, that's all the part about product evolution I will introduce. And of course, we still have much work to do, and which will be shared by Zhong Liang. Thank you.
Okay, of course, our data lake, VolueJ, has minutes to go. While space everywhere, here's the roadmap. In data infrastructure of Kuaishou AI scenarios, future blueprint is in 4 acts. One is ecosystem epoxing. Swallow semi-structured, unstructured bits, think AI mega models, scaling from PB to EB. Data types now including text, vectors. 2. Language liberation. Break Java jail. C writers welcome. Both the data lake adoption from 20% to 17%, of AI pipeline through polyglot signature. 3. Turbocharged performance. Morph into an analytical powerhouse, building indexing cloud-native engine. Latency slashed from minutes to seconds. One circle interface to raw or queries. 4. Scenario evolution. Here offline analyze logical white tables, resurrect real-time survey, cutting results blocked by 13%. Today's presentation comes to an end here. By now, we should have gained a clear understanding of Kuaishou Hudi implements practices in AI scenarios. If there had any technical points from our earlier discussion that remain not clear, or special aspects you wish to explore future, we welcome your questions during the Q&A sessions. Let's now open the floor for discussions.